Hi everyone, so this is our first lesson after our review. This is lesson 1.1, and we're going to leave off where your previous course finished and talk about the derivatives of sine, cosine, and other trigonometric functions. So we've talked about derivatives and integrals using the basic formulas, the product rule, the quotient rule, the chain rule, the power rule, etc. So now we're going to look at some more or different functions or advanced functions. And the first one is trigonometric functions. And the ones you're going to think of right off the bat, sine, cosine, and tangent. So the first one I want to look at is sine. Okay, but to do that, you kind of need to look at both the sine and cosine curves if you graph them. Okay, so our first graph on the left here is sine. Okay, so starting off, okay, if you had 0, this is in radians, okay, but the same would count as 0 degrees. Sine of 0 is simply 0, okay. Cosine, on the other hand, at 0 degrees, okay, or 0 radians, the value of cosine is actually 1, okay. So when you combine them, you can see that they're out of phase. Okay, in other words, if you were to shift the cosine graph at 90 degrees, or if you talked in radians, okay, so 90 degrees, or in radians, pi divided by 2, okay, that is the shift you'd have to do to make them look the same. So in other words, if you shifted the cosine graph by 90 degrees, you would have the exact same graph overlapping sine. Okay. Now the reason that that is important is because we're going to now look at this in terms of derivatives. So I showed you this just purely based off of graphing this function and what it looks like. Okay, both of them are waves, right? Meaning that they repeat each other. In fact, every 360 degrees or at 2 pi radians. But in terms of a derivative of a function is the slope of the tangent, okay, at each point in time in that curve, okay. So if we start off looking at the sine curve, I'm going to focus on 4 points. 0, when it's at its peak or maximum, which is at 90 degrees. When it goes back to 0, which actually it would be at 180 degrees. When it goes to its minimum, or its maximum point kind of in the negative direction at 270 degrees. And our final point at 360 degrees. In other words, okay, once it's made a full revolution. So the slope at each of these points is relatively simple. Okay, you can see in the sine, at the start, it's in the positive direction. Okay, it actually ends up being a value of 1. Okay, but that's not necessarily important. You'll see it's in a positive direction. When it gets to the very top, the slope of that line, tangent to it, would actually be 0. When it gets back to 180 degrees, the slope of the line would actually be the same as it was at the starting point, except that it's negative, right? Because it's going in the opposite direction. And back down at its minimum, again, we're back at a straight line, which is 0. And this cycle is going to repeat, right? You get to the last point, 360 degrees. And remember, since these are wave functions, that cycle is going to continue to repeat. So I've showed you each of these because I want you to compare them to the values that are in the cosine graph. Okay, so at the exact same point in time. So at point 0, okay, you can see that the value of your cosine function is 1. When you get to 90 degrees, or it's about halfway between point 1 and 2, you can see that the value is 0, which is the same value as the slope, okay, of the sine curve at that point. Next, you can kind of see, okay, at the third point here, the slope is negative, but around the same as the sine, right? And it's negative here. At your fourth point, okay, the slope again is at 0. Okay, tracing that out, the same point here, you see that the point is 0. So what this shows, all right, is that the cosine graph, the values you obtain are the same as the slope values that you're obtaining on your sine graph. Okay, so what this actually means is the derivative of sine is actually cosine. Okay, so it's a relationship that's easier to see when you actually see it in terms of these functions graphed, as opposed to in the past when you might have seen this done as a limit. Okay. So like I said, and kind of like we saw in the last slide, the derivative of sine with respect to x is cosine. Okay. So this first equation applies if it's just simply x. Okay. Not 4x, not x squared, okay? Just x. If you have something else in the brackets, let's say it's sine of 2x to the exponent 4, then remember back to derivatives, we can apply the chain rule, okay? So what we do for the chain rule is whatever's inside the brackets, we can assign it a letter like u. So we can say let u equal 2x to the 4. So in the case of using the chain rule, we can have a function y equals sine of 2x to the 4. And if we let u equal 2x to the 4, then our function is y equals the sine of just u. So when we do the chain rule, you have to do two derivatives multiplied together. So the derivative of this function, sine u, would be the derivative of just sine u with respect to u, multiplied by the derivative of that function u with respect to x, that function being the 2x to the 4th that we started with. So if we did this in this case, the derivative of sine u is simply cosine of u. And du by dx, the derivative of 2x to the 4th is 2 times 4x to the 4 minus 1, okay, using the power rule. So what we end up with is if we simplify this, we get 2 times 4 is 8, x cubed, times the cosine of u. So we can now substitute our original value back in, which is cosine of 2x to the exponent 4. Okay, so for most instances, you're going to have to do derivatives this way. Okay, so making sure you use that chain rule in order to calculate this. Okay. So let's look at a few examples. So I'm going to actually do 3 separate examples of just the sine function with slightly different variations so you can see how the derivatives change. So the first is find the derivative of y equals sine of 2x cubed. Okay, so you just saw a similar example from me last slide. And you'll notice in here that in the brackets for the sine function, it's not just x. Okay, it's a different function. So like I said, every time you have to use the chain rule to solve these ones. So I'm going to let u equal 2x cubed. So if I substitute that in, y is equal to sine of u. So now taking the derivative using this chain rule, dy by dx is equal to this function y, derivative of y with respect to u, okay, the function that we named, times du by dx. So if I substitute this in, dy by dx is the derivative of just sine u, which is cosine u. And that's multiplied by the derivative of the function u by dx, which is the derivative of 2x cubed, which is 2 times 3, okay, x to the 3 minus 1, bringing that power down and behind it. So if we simplify this, 2 times 3 is 6, x squared, because it's x to the 3 minus 1, times the cosine of u, okay? But in this case, u, we can now write as the function of x again. So instead, we write cosine of 2x cubed. That's just substituting the value of u in, okay? So our next example is going to use two different rules, okay? So it's going to get a little more difficult. Find the derivative of y equals x squared sine of 4x. So in this case, you have two functions multiplied together. So in this case, you have to use the product rule. And the product rule, remember, is when you have two functions multiplied together, again, you set them to be certain variables. So I'm going to let u equal x squared and v equal sine of 4x. So if I substitute those in, I get y is equal to u times v. So if I use the product rule, okay, dy by dx is equal to the function u multiplied by the derivative of the other function, dv by dx, plus the function v times the derivative of the other function, du by dx. Okay, so that's using the product rule. So now we can simply substitute these values in, because we know the values of u and v, and we can calculate the derivatives using our normal rules rather easily. So our first one is u, which is just x squared, multiplied by the derivative of function v with respect to x. So that derivative is simply cosine of 4x. Okay, using again that chain rule. So now we have to multiply it by the derivative, the area in the brackets, which is simply 4. Okay, and that's plus our function v, so sine of 4x, multiplied by the derivative of the function u, so which is simply x squared. So the derivative would be 2x. So if I simplify this, dy by dx is equal to 4x squared cosine of 4x plus 2x times the sine of 4x. Okay, so this added two different rules together. So you'll see, in this case, because we had the functions multiplied together, that piece was the product rule. But then when we did the derivative, okay, of this function, the sine of 4x, I'll actually show it in a different color. Because it wasn't just x in the brackets, what we did here was actually the chain rule. Okay, so what I'm showing you that just to show you how these rules apply. So it's kind of isolating each piece to see how these puzzles fit together. Okay, as always, you can walk through this example by pausing it and replaying it, but you can also ask questions about them during our tutorial sessions. Okay, so our third example is a little bit different, okay, because it has sine that's squared. So find the derivative of y equals 4 sine squared of x. Okay, so I like to approach this by changing this function to be something that's easier for us to differentiate, going back to the basic principles of derivatives that we've learned. So when you see sine squared of x, that's the same as sine times x, sine of x times sine of x. Okay, so that's actually equal to sine squared of x. Another way you could write this is you could write this as y equals 4 times the sine of x squared. Okay, The reason I like to write that is then we can easily apply the chain rule to this problem. Okay? So if we do that, okay, I'm going to let u equal sine of x. So this becomes y equals 4 times u squared. So using the chain rule, dy by dx is equal to 4 times the derivative of u squared, which is 2u, times the derivative of the function u with respect to x. Okay? So if you do that, dy by dx equals 4 times 2 is 8, so 8u, multiplied by du by dx. And the function u is simply sine x. The derivative of sine x is simply cosine x. Okay? So if I substitute in u, then dy by dx is simply 8 sine x cosine x. Okay? And that's just, again, using the chain rule. Okay? So starting with a function that's a little bit more manageable, and then these derivatives, okay, become far simpler when you approach it that way. Okay, so the first item we looked at was the derivative of the sine function. So now I want to start with the cosine function and find its derivative. Okay, so remember the derivative is the slope of the tangent, okay, at each point of your function. Okay, so starting with cosine at point 0, our slope is 0, and hey, it lines up with the sine function. At the next point, our slope is negative, because it's going in the downward direction, so it's negative. And what you'll see here is that it's actually showing positive 1 on the sine function, so a little bit different. At our next point, okay, again, we're at 0 for a slope at the very bottom of the cosine curve. And what do you know? We're back at 0 here. Moving to our next function, you can see we're sloping in the positive direction. And you'll see here at that same point, we're at negative 1. And then ending the cycle, we're again at a slope of 0. Okay? So what you'll notice here is we were backwards to it, right? So when the slope of the cosine curve was negative, the value of sine was positive. And when the slope of the cosine curve was positive, the value of sine was negative. Okay? And what that means simply, other than that, the points were equal, right? When it was equal to 0, it was 0 in all 3 spots, right? And that's because 0 is not positive or negative, right? But what that means is the derivative of cosine x with respect to x is simply the negative of the sine function. So negative sine x. Okay? So slightly different, just adding that negative sign to it. Okay. So like I said, and this is consistent with how we looked at the sine function, this first equation, the derivative of cosine of x is simply the negative sine of x. That works when the function in the brackets is simply x. When it isn't, okay, just like if, for example, if it's the cosine of 4x squared, then again you have to use the chain rule, okay? Nothing different applies. So in this case, you would have the derivative of your function cosine with respect to x is equal to the derivative of cosine. In this case, I let u equal this function. In this case, let's say it's 4x squared. So it's the derivative of cosine u with respect to u times the derivative of u with respect to x. Okay, so what you're always going to end up with as an answer is the negative sine, okay, of that function u times the derivative of that function du by dx. Okay, so let's look at our first example using that formula. So find the derivative of y equals cosine of 4x plus 3. Again, what's in the brackets here is not simply x. Okay, it's 4x plus 3. So we know we'll have to use the chain rule to solve this. So I'm going to let u equal 4x plus 3. And you don't have to use u. I like to be consistent in all of my problems and usually use terms like u and v. I just find it helps to eliminate a lot of confusion. So if I substitute u in, I get y equals the cosine of u. So looking very familiar to our last slide. So using the chain rule, the derivative of y with respect to x is equal to the derivative of cosine u with respect to u times du by dx. Okay? So dy by dx is equal to the derivative of cosine of u is negative sine of u multiplied by the derivative of the function u with respect to x. So the derivative of 4x plus 3 is simply 4, right? Because the derivative of a constant is 0, and the derivative of 4x is simply 4. So this just becomes 4. So now substituting the value of u in and simplifying, dy by dx is simply equal to negative 4 sine of 4x plus 3. Okay, so identical in how we approach this as the sine function, okay? Just a different derivative formula to know. So let's look at another example. Find the derivative of y equals cosine of 2x squared plus 3x. Okay, again, it's not just x here. So we have to use the chain rule. So let u equal 2x squared plus 3x. So if I substitute that in, y is equal to the cosine of u. Now using the chain rule, dy by dx is equal to the derivative of cosine of u with respect to u times the derivative of the function u with respect to x. So if we take the derivative, du by dx is equal to 2 times 2 x to the 2 minus 1 plus the derivative of 3x is simply 3. So simplifying, we get 4x plus 3. Okay, depending on where you are, you may either want to do all the steps like in the first example, or immediately go to your derivative answer like I did for the derivative of 3x. Either way that's easier for you is fine with me. Okay, I mean, the more work you show, the easier it is for me to grade your papers, but either way works for me. I will usually be able to follow your logic. So if I substitute this in, this should say du by dx. If I substitute those in, dy by dx is equal to the derivative of cosine is simply negative sine u. And we just calculated du by dx. It's 4x plus 3. So if we substitute these all the value in for u, then dy by dx is equal to negative 4x plus 3 times the sine of 2x squared plus 3x. Okay, so as you see more of these examples, you should start to notice the similarities to when we did regular derivatives using these rules like the chain rule. Okay. So our last example, we find the derivative of y equals 3x squared plus 2 times the cosine of 4x. So you'll see here, two functions multiplied together, meaning we have to use the product rule. And you'll also see that cosine, okay, is not just x in the brackets. So we'll have to use the chain rule for that function. Okay, so starting with the product rule, I'm going to let u equal 3x squared plus 2 and v equal the cosine of 4x. Okay, so just setting them to each one of the functions in the initial equation. So if I substitute those in, y is equal to u times v. So using the product rule, dy by dx is equal to the function u times the derivative of the function v, plus the function v multiplied by the derivative of the function u. Okay, so we can actually do this two ways. We can do the derivative directly in our answer, or we can calculate the derivatives on the side here and then just substitute all of our values in. Okay, so I'm going to do it the second way. So we'll start with the derivative of the function u, so du by dx, and that's equal to 3 times 2x to the 2 minus 1. And the derivative of the constant 2 is just 0. So du by dx is simply 6x. The function v, okay, so dv by dx is equal to, okay, derivative of cosine, negative sine of 4x. And remember, using the chain rule, it's multiplied by the derivative of the function within the cosine brackets. Okay, so in that case, the derivative of 4x is simply 4. So for simplifying this, we get the negative 4 times the sine of 4x. Okay, sorry for my bad number there. That's better. So if you do it this way, you can simply just substitute all these values in. Okay, so if we do that, dy by dx is equal to u, okay, which is 3x squared plus 2, times dv by dx, which is negative 4 sine 4x, plus the function v, cosine of 4x, times the derivative of the function u, which is simply 6x. So if I now simplify this, dy by dx is equal to negative 4 times 3x squared plus 2 sine 4x plus 6x cosine of 4x. Okay, I just like putting the terms, like the numbers first and then the functions with variables first. Again, that's just preference for me. If you had left it as this answer, that would still have been acceptable to me. Okay? So knowing the derivative of sine and cosine opens up windows for other trigonometric functions to figure out the derivatives. Okay? The first one is the tangent function. So if you remember back for tangent, it's actually equal to the sine of a function divided by the cosine. And for those functions, remember when you have one function divided by another, you can use the quotient rule to find the derivative. Remember, the quotient rule is if we let u equal to sine x and v equal to cosine of x, then our function, okay, tan of x becomes u divided by v. And the quotient rule, so if we take the derivative, the quotient rule, the derivative of tan x with respect to x, uses the quotient rule. So the quotient rule is the function v times the derivative of the function u with respect to x minus the function u times the derivative of the function v with respect to x divided by the function v squared. So we know simply the derivative of the function u, du by dx, is simply cosine of x. And the function v is cosine, so the derivative of the function v is simply the negative sine of x. Okay, we just established those in our previous slides. So now I can substitute those values in. So the derivative of tan x with respect to x is equal to the function v cosine of x times the derivative of the function u, which is the cosine of x, minus the function u, okay, which is sine x, times the derivative of the function v, okay? The derivative of the function v is negative sine x. And that's divided by the function v squared. Okay, so the function at v is cosine of x squared. So what we're left with here is the derivative of tan x with respect to x is equal to cosine squared of x plus sine squared of x divided by cosine squared of x. So now to solve this, okay, we have to dig back to an original trigonometric identity here. Okay, and what that is that sine squared x plus cosine squared x is equal to 1. Okay, it's kind of one of the basic trigonometric identities that we might start with. So knowing that, we can simply substitute that into our equation. Okay, if you didn't remember that trigonometric identity, that's totally fine. I'm showing you this as a proof, and I don't expect you to be able to do this proof. I'm just showing you how this function was developed. So if we substitute that in, we get 1 divided by cosine squared x. Okay? And what that actually is, if you remember, 1 over cosine of x is secant of x. Okay? So if you substitute that, what that means is the derivative of tan x with respect to x is simply secant squared x. Okay? If, again, you don't just have x in your function, let's say it's 4x or 2x squared, something like that, then again you have to use the chain rule. So the derivative of it, okay, if you let that function be u, the derivative of tan with some function u with respect to x is equal to secant squared of that function u times du by dx. Okay, so that's again following the same chain rule that we did for sine and cosine. Okay, so that's the tangent function. We're going to look at one example of this, and then I'm going to show you a couple more derivatives. I won't show you this type of derivation. I'm just going to show you what the derivative is so that you know what it is when you're solving problems. Okay, so let's look at an example using the derivative of the tangent function. So find the derivative of y equals tan of 5x plus 2. Okay, so we know that first of all, this is not just x. Okay, so we're going to have to let u equal 5x plus 2. So our function becomes y equals tan of u. So using the chain rule, dy by dx is equal to the derivative of tan u, with respect to u, times the derivative of the function u with respect to x. So the derivative of the function u with respect to x is simply 5, because it's the derivative of 5x plus 2. So the derivative of a constant is 0. The derivative of 5x is just 5. So substituting these in, okay, dy by dx is the derivative of tan, which is secant squared times u, multiplied by phi, the derivative of u with respect to x. So substituting u in, our derivative is equal to 5 times the secant squared of 5x plus 2. Okay? So after we've seen kind of the major three, the other three, I'm going to just show you what the derivatives are. Again, I'm not going to expect you to solve these proofs. But as you get into more complicated functions, so these three are secant, cosecant, and cotangent. Okay? So remember, when you have these, secant is 1 divided by cosine of x. Cosecant is 1 divided by sine x. And cotangent is 1 divided by tan x. Okay? Their abbreviations as shown below. Secant is SEC, cosecant is CSC, and cotangent is COT. Okay? And you'll see in these derivatives that there's a variety of different functions that end up coming into play here. So the derivative of secant with respect to x is secant times tangent. If the function is not just x, again using the chain rule, you have to add the du by dx term, okay? And that's letting u equal the function in the brackets. The same applies for cosecant and cotangent. So the derivative of cosecant is equal to negative cosecant of x times the cotangent of x. Again, these are just starting to get more and more complicated with more terms being added in. And again, if the function in here is not simply x, you must, using the chain rule, add the du by dx term on at the end. For cotangent, the derivative of cotangent is simply the negative of cosecant squared x. Again, if it's not just x in brackets, you must add du by dx to your derivative using the chain rule. Okay, so again, I'm just showing you these. This is kind of a reference slide for you to use when you're practicing later questions. So I'm going to do 2 examples using other functions to end off this lesson. Okay, so the first example, find the derivative of y equals the secant of 5x squared plus 3x cubed. So we know, okay, this is not just x, so we'll let u equal 5x squared plus 3x cubed. And to make it simple, because we're going to need it, we'll do du by dx now, so we can substitute it into our equation later. So that's equal to 5 times 2x to the 2 minus 1, okay, using the power rule, plus 3 times 3x to the 3 minus 1. And if we simplify this, du by dx is equal to 10x plus 9x squared. So we know from our previous slide, all right, that the derivative of secant, okay, is secant x. Sorry, I will write it different. The derivative of just secant of a function with respect to x is equal to the secant of the function times the tan of the function times du by dx. Okay? So knowing that, we can simply substitute these values in. So derivative of secant with respect to x is equal to the secant of u, 5x squared plus 3x cubed, times the tangent of u, 5x squared plus 3x cubed, times du by dx, which we already calculated, 10x plus 9x squared. Okay, so it's not that it's a difficult derivative if you know the formula, it's just that the answers start to become very, very long. Okay, you can see how our starting function was just the secant, that function, and now it grew as we took the derivative, and you'll see that with these more advanced trigonometric functions. So our last example, find the derivative of y equals 3x squared plus 4 times the cosecant of 2x plus 3. So first thing you notice, two functions multiplied together. Okay, so that means you'll have to use the product rule. So if we let u equal 3x squared plus 4 and v equal cosecant of 2x plus 3. Okay, so remember, for the product rule, we substitute this in, we get y equals u times v. So the derivative is simply u times dv by dx plus v times du by dx. So again, to make it easier, I'm going to calculate the derivatives on the side here so we can just substitute them in. The first derivative, du by dx, okay, is simply 3 times 2, x to the 2 minus 1, and plus 0. Remember, because the derivative of a constant, in this case 4, is 0. So simplifying this, du by dx is equal to 6x. The derivative of cosecant, so we'll call that function v, like we did, dv by dx. And again, I'm going to write it down. You can reference the previous slide, or if you have a printout of it, just to know this. But the derivative of cosecant is negative cosecant of the function 2x plus 3 times cotangent, okay, of the function 2x plus 3. But remember, the function in here is not just x, so we have to take the derivative of that function too. So I'm actually going to just give us some more room. Okay, so just writing what we just had, dv by dx is negative cosecant of 2x plus 3 times cotangent of 2x plus 3. And the derivative of 2x plus 3 is simply 2. Okay, sorry I had to erase that. This just makes it a little simpler. So now we can substitute each of these values into our final equation. So dy by dx is equal to u, 3x squared plus 4, times dv by dx, which is negative cosecant of 2x plus 3, times cotangent of 2x plus 3 times 2, plus the function v, cosecant of 2x plus 3, times the derivative du by dx, which is 6x. Okay, there's really not much simplifying to do here. I'm just going to collect some terms and change the order. But our final answer is then negative 2 times 3x squared plus 4. All I'm doing is rearranging. Cosecant of 2x plus 3, cotangent 2x plus 3, plus 6x times cosecant of 2x plus 3. Okay, so don't let how long this final answer is kind of intimidate you when you're doing these derivatives. Remember, all we did was do steps. Okay, the function in this case, we had the function u and v. We took the derivatives of those two functions and simply substituted them in. The final answer is the final answer. Okay, it's more about the process of did you do these steps correctly. After that, it's simply just substituting these values in. Okay, so that's it for this lesson. Okay, I've given you a few practice problems. You can try other ones that are slightly more complicated than what we've seen. You might have seen in our class. And when I say more complicated, it might just have some different variables, maybe a square root or something like that. Again, a square root, if you remember, is just an exponent. So you can try those other ones as well. The ones I picked out here, I do recommend you give a try. If you do have questions, please send me an email or join me for a tutorial. Thanks, everybody.